The number of intelligent civilizations in the universe equals the number of habitable planets, multiplied by the probability of life's emergence, multiplied by the probability of intelligence appearing among life. If you stand up and look at yourself in the mirror now, from the point of view of matter, you will see some imperfection. To understand what I'm talking about, I must debunk a very popular myth about matter itself. Take water, for example. When frozen, it turns into ice, acquiring a crystalline form. Since early childhood, we sincerely believe that ice crystals or snowflakes or patterns on frozen windows are examples of spontaneously occurring symmetries in nature. Examples of the emergence of some harmonious structure in contrast to the prevailing disorder and chaos in nature. But in reality, it's the other way around, or rather, the exact opposite. A crystal is not an emergence but a breaking of symmetry, because water is much more isotropic, meaning it's much more uniform and symmetrical in all directions than ice. When water crystallizes, atoms in it self-organize into clear patterns. The space occupied by the crystal loses its symmetry, so the crystal disrupts spatial uniformity, creating repeating patterns in certain directions. Glancing across our entire universe, you will notice the same thing. The universe is quite uniform. It doesn't matter where you are, here, or here. On average, you will observe roughly the same picture. Regardless of the observation point, if you look out the window at the starry sky, you will find that the part of the universe that we can see is a good example. If you looked out the window while on the other edge of the galaxy, you would see roughly the same thing. But if the universe is so uniform, then what are you doing here? Just as ice breaks the symmetry of water, galaxies, stars, and planets also break the symmetry of the universe. However, nothing disrupts it with its existence as strongly as a human being. Stanislaw Lem, in his monumental work, Summa Technology, poses the question, is our civilization a common or exceptional phenomenon? Do we conform to the norms of development accepted in the universe, or are we a deviation? We understand how and why the process of water crystallization occurs. We understand how and why various celestial bodies arise, but don't be fooled. We have no idea how and why we appeared. Think about it. Just mentally move yourself million light years in any direction from where you are and look around. The universe is generally the worst place imaginable for human existence. It's absolutely unfit for that. Is there even a place in the universe beyond Earth where one could teleport and not die? We may be the result of such a fortunate or unfortunate coincidence that the likelihood of it is one in the entire universe since its inception. At least, that's what paleontologist Peter D. Ward and astronomer Donald Brownlee assert in their book, Rare Earth. In this book, they present arguments about why complex life is an incredibly rare or even unique phenomenon, requiring exceptional astrophysical and geological coincidences. This video is largely based on this book. Tell me honestly, how many times have you heard that Earth is the most ordinary rocky planet in a typical planetary system, located in an unremarkable region of one of countless galaxies? Carl Sagan and Frank Drake love to repeat this. Along with many scientists, they believed that, considering all the unremarkableness of our dwelling place, and considering that there are countless Earth-like planets, life in the universe must be an absolutely ordinary phenomenon. This point of view even has a quite characteristic name, the mediocrity principle. But what about the reverse approach? What about the idea that our Earth is fantastically special? What about the idea that the solar system is not a typical cosmic construction, but an unfathomable rarity? Could it be that even the galaxy we find ourselves in is not just an ordinary case? What premises led to the emergence of such a strange form of matter called humanity? From the author's point of view in Rare Earth, it's not as straightforward as one might think. Earth is not just another rock in space, and space may be as empty as it appears. The hypothesis of a rare Earth is tinged with the chill of loneliness and even the meaninglessness of what's happening. Proponents of the rare Earth hypothesis argue that a planet capable of supporting complex life must inevitably be more or less similar to the solar system. Many are convinced that almost the only condition for the emergence of life on a planet is its location in the circumstellar habitable zone. This is an area around a star where conditions on the planet's surface will ensure the existence of liquid water. Liquid water is an essential condition for life, as it serves as a solvent in many biochemical reactions. The uniqueness also lies in the fact that Earth's orbit around our Sun is quite round, meaning we never find ourselves too far or too close to the sun. Many believe that if you find rocky planets in space that orbit their stars in the circumstellar habitable zone, life on these planets can be discovered with a very high probability. But for life, as you'll soon understand, this is catastrophically insufficient. From the author's perspective in Rare Earth, the habitable zone within a star is not the only habitable zone in which one must find oneself. Our entire solar system was very fortunate to find itself in the habitable zone of an entire galaxy. This is not the most obvious thought. Our solar system rotates around the center of the galaxy at a rate of one full revolution, approximately every 235 million years. That is, since the appearance of oceans on Earth, it has covered this distance 17 times. Since the appearance of the first reliable traces of life, 15 times. Since the emergence of the first cellular organisms, about 7 times. But this is not just a relaxing flight. The vastness of the galaxy harbors many terrifying things that are absolutely deadly to our tiny solar system, especially over such a long period. Yet living matter is still here. You see, most of any galaxy is a dead zone, unable to support complex life. The closer to the center of the galaxy, the stronger and more devastating the effects of X-ray and gamma radiation. They are generated by black holes and neutron stars, which are more numerous the closer we are to the galactic center. The closer we are to the galactic center, the more often supernova bursts occur somewhere nearby, capable of destroying entire worlds from a distance of many light years. There are many stars and galaxies, and even more planets around these stars. Therefore, life must be spread throughout the Milky Way. But when we say this, we are greatly mistaken, because the bulk of the stars are concentrated closer to the center, which is not surprising, but it is precisely in the center of the galaxy where most various activities occur. In addition, the high density of stars near the center of the galaxy also means greater gravitational disturbances. That is, even if a planet is orbiting its star at an optimal distance, this delicate balance will be disrupted when some other star flies nearby. We can conclude that being too close to the center of the galaxy is bad. However, being too far from the center is also bad. Moving away from the galactic center reduces the metallicity of stars, and metals are extremely necessary for the formation of Earth-group planets. Recent research indicates that the extent of the galactic habitable zone is from 7 to 9,000 parsecs from the center of the Milky Way. To put it simply, this zone includes no more than 10% of stars. Other studies say that only 5% of stars are suitable for the birth of life. But the most important thing is time. A planetary system suitable for life must stably maintain favorable conditions for billions of years for complex life to develop on it. Therefore, a star should preferably have an almost perfectly circular orbit around the center of the galaxy, and moreover, its rotation speed should be synchronized with the rotation speed of the spiral arms to pass through dense clusters of stars as rarely as possible. And yes, the solar system is in the habitable zone of the entire galaxy, and the Sun's orbit around the center of the Milky Way is almost perfectly circular, with a period of 235 million years, which roughly corresponds to the rotation period of the galaxy. So our planet was lucky to be in the habitable zone of its star system, which in turn was lucky to be in the habitable zone of its galaxy. But that's not all. Our entire galaxy is a fairly rare case. 10 billion years, approximately how long the Milky Way has not collided with other galaxies. Our galaxy is anomalously quiet and dim. Only 7% of galaxies in the observable universe are like this. As you can see, even on such a large scale, there are many nuances that need to be taken into account if we want to understand how unique our case is. However, most of the mysteries and unimaginable coincidences are not far away in space, but right here within our solar system. Looking at the stars, we imagine that if we were to fly closer to these points in the night sky, they would look roughly the same as our sun. Of course, we all know that stars can differ radically, for example, in their size, but this is not about that, but about the fact that, according to scientists' estimates, more than 50% of star systems in our galaxy are at least binary. That is, in half of the cases, if you approach the stars that you see, you could observe something like this. For example, the North Star, one of the most famous stars, which has helped travelers find their way for many centuries, is not a single star. It is a triple star system. Binary and triple star systems look impressive, but they are almost absolutely unsuitable for life. In systems where there is more than one star, the stability and resilience of planetary orbits is a big question. A very fine tuning or some special conditions are needed for even a lifeless planet to normally exist among binary or triple stars. Thus, we can cross out more than half of the stars from our list of potentially habitable ones, and this is just the beginning. Our Sun is unique in many aspects itself, because even if there is only one star, it is still no guarantee of stability. For life to develop, a star must be very stable. The Sun has a low luminosity variation of only 0.1%. It is common to say that the Sun is the most ordinary star, of which there are countless. But to this day, not a single solar twin has been found in terms of luminosity size, temperature, age, and metallicity. I remind you that the correct metallicity is needed for the formation of the protoplanetary disk from which planets are formed, and also for the small change in the star's brightness. You might say, is the Sun some sort of absolute ideal? There are plenty of options. For example, the larger the star, the wider its circumstellar habitable zone, and therefore the higher the likelihood of the emergence of life itself. If we're talking about temperature, you would be right, but the larger the star, the stronger its ultraviolet radiation level, and the faster it will burn all its fuel and turn into a red giant. For example, the star Betelgeuse is only 10 million years old, and it will soon explode. The Sun is 500 times older than Betelgeuse. Ignoring radiation, even the simplest life near supermassive stars is likely to not have time to develop. But there are also red dwarfs. They have weak radiation, and they live much longer than the Sun. A red dwarf with 10% of the solar mass will burn for 10 trillion years, an unimaginable amount of time, and red dwarfs never become red giants. This is all true, but red dwarfs are quite cold and very dark. Their temperature is only slightly higher than the temperature of a filament in an incandescent lamp, about 5,400 degrees Fahrenheit. Some red dwarfs emit 10,000 times less light than the Sun, so a planet with the potential for developing complex life has to be very close to such a star. And it seems cool. But there are at least two problems. Firstly, a planet, having approached a red dwarf so closely, will almost inevitably fall into tidal locking and will rotate around the star, facing it forever with only one side. For example, this happens between the Moon and Earth. Thus, on one side of the planet, it will always be monstrously hot, and on the other, monstrously cold. The second problem is that the stellar wind from red dwarfs is not much weaker than that from the Sun, and being so close to the star, this will leave no chances for life to develop in the terminator zone. The terminator zone is a strip between the illuminated and dark part of the planet, where the temperature theoretically can be comfortable. Now take a look at the planets in our solar system. Do they look normal? Is there anything unusual about them? How about their placement? Is this a typical arrangement of planets in planetary systems in the universe? We have 4 small rocky planets, followed by gas giants. Perhaps this is a widespread phenomenon, but no, we actually have a very strange planetary system. Firstly, it has the strongest range of planetary characteristics, starting from tiny Mercury and ending with gigantic Saturn and Jupiter. In most planetary systems in the universe, planets don't differ much from one another. Most planetary systems in space near stars have super-Earths. A super-Earth is a type of exoplanet with a mass higher than Earth's, but substantially below those of the solar system's ice giants. But in our solar system, there are only a few small rocky planets. Secondly, gas giants the size of Jupiter or Saturn are quite rare, found in only 10% of planetary systems, and they rarely have stable, nearly circular orbits so far from their star. And we have 2 gas giants with nearly circular orbits at a considerable distance from their luminary. We still don't quite understand how such a configuration of the solar system's planets came about. Someone might irritably ask, well, what does such a layout give us? But it gives us quite a lot. Unlike most super-Earths in space, Earth's size is optimal. A planet that's too small, among other things, cannot support a sufficient atmospheric layer, causing its surface temperature to be low and variable, and oceans simply will not be able to form. If the planet is too large, it will retain a very dense atmosphere. Wait, Venus, despite being smaller, has an atmosphere 92 times denser than Earth's, making the temperature there around 900 degrees Fahrenheit. This is true, and possibly Earth once had a similar atmosphere. But then perhaps it lost it due to a catastrophic impact that formed the Moon. This impact later allowed Earth to acquire an atmosphere with optimal parameters. Its density perfectly compensates for the daily temperature fluctuations. The ozone layer effectively protects Earth's surface from ultraviolet rays. Nitrogen and carbon dioxide are in the right proportion for life to emerge, precipitation necessary for the water cycle, and so on and so forth. Such a distribution of planets, where gas giants are on the outer side of the planetary system, provides an advantage as a shield against asteroids. Take Jupiter, for example. I always thought it was just a slightly more massive Saturn. But as it turns out, Jupiter is a gas giant with a mass that exceeds the mass of all the other planets in the solar system, combined by more than 2.5 times. It is probably the reason why the hypothetical Oort cloud with trillions of comets is at a great distance beyond the orbit of Neptune and not bombarding the Earth. Scientists suggest that objects in the Oort cloud formed close to the Sun, but Jupiter's gravity and that of other gas giants hurled them to the fringes in the early stages of the solar system's evolution. Moreover, if debris from the outskirts of the solar system decides to head towards its center for some reason, they are highly likely to run into one of the gas giants first. For example, 30 years ago, Jupiter took the hit of a 12-mile wide comet, previously tearing it into separate fragments. Such a collision would likely have sterilized Earth. Jupiter often attracts all sorts of unpleasant cosmic debris to itself. In 2009, a celestial body left a black spot in Jupiter's atmosphere the size of the Pacific Ocean. In 2021, amateur astronomers captured the collision of an unknown object with Jupiter. Let me remind you, Jupiter, this huge gas giant, comes right after Mars, meaning just after the Earth group planets. If this gas giant with the strongest gravity had a less circular orbit, the solar system would likely look entirely different and probably without us. Just imagine, Jupiter's movement is so optimal that it manages to reside between two opposites, specifically between the second heaviest from the end and the second heaviest from the beginning of the solar system's planets, and it doesn't exert significant gravitational effects on either one. I'll simply note that the above factors not only together but also individually had critical importance for the emergence of complex life on Earth. Remove any one of them, and humans likely would not have appeared. And how many variables remain unclear? The authors of Rare Earth list only what's more or less on the surface. For example, Earth's massive core, it's somehow larger than expected. And apparently, this is related to our moon. Just look at the other rocky planets of the solar system, Mercury and Venus. They have no moons at all. Look at Mars' moons, Phobos and Deimos. They are not even spherical, as they are not moons but simply asteroids captured by gravity. Phobos' diameter is 14 miles, and Deimos' is only 7 miles. The Moon is the largest natural satellite in the solar system relative to the size of its planet, making up 27% of the Earth's size. Pluto, which until 2006 was considered a classical planet, is about 6 times less massive than the Moon. The formation of such a satellite is a mystery in itself. It was discovered that samples of lunar rock taken by Apollo astronauts are suspiciously similar in composition to Earth's crust, so the best theory for the Moon's origin that we have so far is Theia. Theia is a hypothesized ancient planet, the size of Mars, that presumably collided with Earth about 4.5 billion years ago. During the impact, Theia's core and mantle mixed with Earth's core and mantle. It's quite likely that we have 2 planets under our feet, hence the large Earth's core. The fragments from the impact formed the Moon. So, what does this mean? It means that a large satellite causes tides. Darwin hypothesized that the simplest life originated in one of the basins created by tides induced by the Moon. Moreover, some scientists believe that after life arose in water, its further spread from the ocean to land was also provoked by gravitational effects. Are these not the tides we're used to? No, this is what the Moon looked like in the sky 4 billion years ago. As you can guess, its gravitational influence was far more terrifying. That is, living organisms were literally constantly thrown ashore from the ocean and died until someone happened to have a useful mutation. In addition, data from 2019 suggests that Theia may have formed in the outer part of the solar system, and most of Earth's water originated there. So perhaps the oceans you see are not native to these places. Rare Earth authors Peter D. Ward and Donald Brownlee note that a large satellite increases plate tectonics, which is necessary for biodiversity and the carbon cycle. Not to mention that the moon contributes to Earth's strong magnetic field, which protects us from cosmic radiation. Additionally, the giant impact on Earth also gave it a special axial tilt and rapid rotation speed. Fast rotation reduces daily temperature fluctuations and makes photosynthesis viable. According to the rare Earth hypothesis, the axial tilt should not be too large or too small, because a planet with a large tilt will experience extreme seasonal climate fluctuations. If the planet has a small tilt or none at all, there would be no seasons, and this would lead to a lack of stimuli for evolution. From this perspective, Earth's tilt is just right. The gravity of a large satellite also stabilizes the planet's tilt. Without this effect, the change in tilt would be chaotic, which would probably make complex life forms on land impossible. There are, at first glance, also completely paradoxical factors. For example, throughout Earth's history, the temperature has fallen sharply twice, and it was completely covered with ice, 2.2 billion and 635 million years ago. It may sound illogical, but these extreme glaciations contributed to the development of life. The first glacial period stimulated the development of photosynthesizing microorganisms, leading to a significant reduction in greenhouse gases in the atmosphere and the release of oxygen. And after the second glaciation, the Cambrian explosion occurred, giving rise to almost all the existing evolutionary branches of animals today. If before this all life was simple and unicellular, then after this there was a sharp increase in the number of complex multicellular organisms. The first brain appears at this very moment. Think about it, if we find a planet in space with ideal conditions, we probably won't discover complex life there for precisely this reason. It's simply not needed there. On a paradise planet, there are no complex survival-related tasks that need to be solved. It turns out that contrasts are needed for the development of complex life, but we don't know in what ratio. Positive factors are not enough. They must be balanced by negatives to stimulate evolutionary processes. But at the same time, negative factors must not be too negative, because life is still a rather fragile thing. So how many factors must converge together in the correct sequence? Let's start small. Suppose we have all habitable zones within a star and galaxy. We have gas giant protectors, we have a rocky planet with water, the necessary atmosphere, and a large satellite, that is, an absolute twin of Earth, somewhere far in space. And what next? Nothing. If you haven't watched my previous video about genes that give us a new perspective on the laws of physics, let me briefly explain that the first smallest unit we call life is a replicator. That is, a molecule capable of copying itself. Only with the emergence of the first replicator do directed mechanisms of evolution begin to act. But the first replicator itself had to appear randomly. Think about it. A complex system capable of copying itself had to appear randomly. That's why we look for the simplest combinations from which this very first replicator could have appeared. But the simplest combinations we see are still too complex for randomness. What is the probability of the appearance of the first maximally simple organism capable of reproduction? So simple that if you remove one element, it can no longer reproduce. Eugene Koonin, a recognized expert in the field of evolutionary and computational biology, in his book Logic of Chance, gives an estimate of the probability of the spontaneous appearance of the first replicator. He calls the chance 1 in 10 to the 1018th power. Now on the screen, you see this number. It is impossible to comprehend how unlikely this event is. One of Eugene Koonin's explanations for how this could be sees the multiverse. Roughly speaking, if there are an infinite number of universes, then the configuration of atoms will also be infinity. In such a case, the realization of a variant with the spontaneous appearance of a replicator is easy to imagine. The emergence of life requires an exceptionally improbable event. Therefore, we are alone in our universe, not only as intelligent beings, but broadly as living entities altogether. I don't want to darken the picture, but I have to. Imagine that the first replicator appears and begins to reproduce. A very important question arises: is the growth of complexity in evolution obligatory? Absolutely not necessary. Some of the first replicators were prokaryotes. These are bacteria and archaea. They were extremely energy inefficient. Due to their construction, they could not store energy in large quantities and become more complex. Here, a simple mutation could not suffice. This is the moment when evolution was not enough. A revolution was needed. Because of this, at the prokaryotic level, development stopped for 1 billion years, or perhaps even more. Nothing foreshadowed more complex forms of life. Evolution could have simply stopped at this stage, but suddenly something happened. Something as unlikely as the appearance of the first replicator. Something that, according to British chemist Nick Lane, could have happened only once in the history of life. An archaeal cell engulfed a bacterium and somehow did not digest it. This bacterium, in the process, deactivated 99% of its genome, got rid of most of its mechanisms, and focused on energy production. Thus, the first mitochondrion appeared. A mitochondrion is a kind of cell power plant. It was this symbiosis, by solving the energy problem, that made the unimpeded complication of life possible. It is thanks to this incredible event that all the life you can see with the naked eye for the same reason exists. I hope no one is tired and you are listening carefully, because the most important part is ahead. The number of intelligent civilizations in the universe equals the number of planets suitable for life, multiplied by the probability of life's emergence, multiplied by the probability of intelligence appearing among life. Intelligence. All of the above does not guarantee the appearance of intelligence. If everything up to this point was theoretical reasoning, we can see this factor with our own eyes here and now. Humanity has described over 1.7 million species of living organisms. Of course, this is not all, and the total number of species currently existing on Earth is estimated at 8.7 million. There are about 500 million extinct species. How many of them were intelligent? I won't talk here about what intelligence is, but in short, we hardly know what intelligence, intellect, and consciousness are. We only have some intuitive understanding. In our own example, we conclude that the appearance of intelligence is possible, but in the example of all other life on the planet, we see that evolution is not particularly inclined towards intelligence. And even more than that, the appearance of intelligence is highly unlikely. Researcher Charles H. Lineweaver asserts that when considering any extreme feature in an animal, intermediate stages do not necessarily lead to inevitable results. A large brain is no more inevitable than the long noses of animals like aardvark or elephants. Monkeys, whales, elephants, dolphins, octopuses, and squids are considered the most intelligent creatures on Earth after humans. Specifically, dolphins are very smart. Their brain is much like a human's, but as Lineweaver notes, dolphins had about 20 million years to build a radio telescope, but they didn't do it. Why are we the only intelligent species on the planet? Aren't you surprised by the fact that evolution, so economical in its manifestations, created the human brain? A device with such a degree of redundancy that it still, in the 21st century, excellently handles the problems of a developed civilization, although anatomically and biologically, it is the same brain as that of our primitive ancestor, who lived 100,000 years ago. How did this enormous prospective potential of reason, this redundancy, as if ready at the dawn of history to begin building civilization, arise in the course of a purely probabilistic evolutionary game by adding two vectors, increasing the number of mutations and strengthening natural selection? What's the probability? Each variable in the equation for calculating intelligent civilizations in space implies the presence of many factors that we try to list. And what do we get? To some extent, we understand how many factors are needed and what they should be like for a planet to become suitable for life. At the same time, we very poorly understand how many factors must coincide for the simplest form of life to form on a suitable planet. And we don't understand at all what factors, in what quantity, and in what sequence are needed for the appearance of intelligence on a suitable planet from the simplest form of life. The absolute majority of factors, as I said, are unknown to us, but let's dream. Suppose we have a formula that guarantees 100% presence of complex life with strict observance of only 80 factors. It sounds very optimistic, but let's make it even more optimistic. Let the probability of each factor not be something like 1 to 10 to the 1018th power, but only 1 to 2, as when flipping an ideal coin. That is, for example, the probability of finding a Sun-like star is not 1 to 1,000 or 1 to 1 million, but 50 to 50%. The probability of finding a rocky planet near such a star is 50 to 50. The probability that it will be in the habitable zone, that it has a moon-like satellite, a suitable atmosphere, and even the probability of the first replicator appearing on it is also 50 to 50%, and so on, until we accumulate all 80 necessary parameters. If our formula is correct and all factors have a 50% probability, then what is the probability under such a layout to meet intelligent brethren? The probability is 10 to the 24th power, or 1 to a septillion. In simple terms, the probability is so exceptionally negligible that you could search the entire observable universe and still not find a single Earth-like planet, not one. In reality, however, there are likely many more factors, and it's unlikely that any of them have as optimistic a probability as with a coin toss. We often hear that claiming we are alone in the universe is too egotistical, but this lofty opinion is unfounded. We have not yet found any evidence of extraterrestrial life, not only intelligent, but of any kind. The hypothesis of a rare Earth is supported by a number of popular scientists, but nevertheless, the book by Peter D. Ward and Donald Brownlee continues to receive its share of criticism since its release. For example, according to recent research and observations, a large satellite is rare for planets in the solar system, but not rare for planets in other star systems. And the arguments that it is essential for the emergence of life raise entirely justified doubts. Moreover, according to a 2008 study, Jupiter caused more collisions with Earth than it prevented. Proximity to a star is not the only way to create a comfortable temperature on a planet. Where do you think there is the most water in the solar system? On Earth. Not at all. Jupiter's moon Europa has twice as much water as Earth. But how is this possible when the average surface temperature on Europa is minus 275 degrees Fahrenheit? It is possible thanks to tidal friction, caused by the eccentricity of Europa's orbit and the influence of other satellites. Under 30 kilometers of ice lies an entire ocean that can reach a depth of 80 to 180 kilometers. The existence on Earth of living creatures capable of living and reproducing in extreme environmental conditions, such as tardigrades, makes the presence of life on Europa entirely possible. And this is despite the fact that Europa is far beyond the habitable zone. Moreover, if we stretch our imagination, we can imagine that on Titan, Saturn's moon, life might have not a water but a methane base. For example, Carl Sagan put forward the idea that non-water-based life is possible even on gas giants. The rare Earth hypothesis predicts that the Sun rarely or never passes through the special arms of the galaxy. However, astrophysicist Karen Masters calculated that the Sun passes through large spiral arms approximately every 100 million years, and some studies even say that several mass extinctions correspond to previous crossings of the solar system through galactic spiral arms. We can doubt almost every point. However, the most important thing is that the rare Earth hypothesis is highly anthropocentric. This hypothesis is not a recipe for creating intelligent life. It's a recipe for creating humans. The book Life Everywhere by English astronomer David Darling was written as a response to rare Earth. He says that the rare Earth hypothesis is not a hypothesis at all, but a fitting of facts to the way life arose on Earth. The question is not whether there is something unusual here on Earth. Every planet in space will have something special. The real question is whether any of the earthly circumstances are not only unusual, but also essential for complex life. Considering that we have no idea what and in what order should be in the equation, considering that we have little idea of what intelligence is and what it can be, why did we even decide that the earthly option is the only possible one? Let's face it, we are looking for not all possible civilizations, but primarily anthropomorphic ones. We bring logic and order to nature through scientific experimentation, and we long to recognize beings like ourselves through such phenomena. However, we do not observe such phenomena. So, do they not exist? Indeed, there is something profoundly saddening in the silence with which the stars respond to this question, a silence so complete as if it were eternal.